All right, let's get right into it. Welcome to today's Explainer, where we're unpacking a genuinely revolutionary concept that completely flips how we view growth, stability, and failure across virtually every scale of reality. We're talking about a unified framework developed by Savio Antonio Vogt called Scale-Regulated Aggregation, or SRA. And trust me, it's a concept that promises to rewrite our entire understanding of complex systems.
So think about this for a second. What actually connects a collapsing star, a catastrophic rocket failure, and a sudden, devastating market crash? I mean, on the surface, these are entirely different domains, right? Astrophysics, aerospace engineering, global finance. But fundamentally, they all suffer from the exact same structural vulnerability, which is unregulated accumulation. They grow, they add up, they compound, and they literally just keep going right until they snap.
But understand how we actually fix this. Here's our roadmap for this explainer. We're going to cover 1. Why complex systems break. 2. Geometry before equations. 3. Solving persistent scientific paradoxes. 4. Stabilizing giant launch vehicles. 5. Macroeconomics and zero-latency computation. And finally, 6. A universal structural law. It's going to be a wild journey from abstract theory to some truly mind-blowing real-world applications.
Okay, kicking things off with Part 1, Why Complex Systems Break and the Limits of Additivity.
You know, for centuries, our traditional physical and economic models have basically assumed that if a local equation works on a small scale, you can just keep adding things up endlessly, and the system will somehow remain stable. But here's the catch. When local validity is pushed beyond its limits, systems diverge into chaos. When a complex system breaks down, it's not actually because the fundamental laws of physics are failing. It's really just our naive assumption that accumulation can happen indefinitely without any structural limitation. A system just can't grow forever in a straight line. Eventually, it hits a breaking point.
Moving right along to Part 2, Geometry before equations. This is the core paradigm shift of scale-regulated aggregation.
Instead of constantly hacking existing equations or inventing new hypothetical entities to explain away anomalies, Vogt argues we've got to first regulate how things add up geometrically. Enter the AM-Regulator. Think of it as the universe's universal structural safety switch. It's a mathematical framework that naturally caps additive growth, forcing geometric saturation before a system can spiral out of control and crash. It essentially tells the system, okay, you've grown enough, it's time to level out. The contrast here is wild. Classical additive models blindly escalate to infinity, which produces divergence and inevitable structural breaks. But the AM-regulated model, it does the exact opposite. It forces that geometric saturation, suppresses variance, and acts as a shield to stabilize the system as it scales up. It smoothly transitions everything from purely additive behavior to moderated multiplicative behavior. So let's look at Part 3, Solving Persistent Scientific Paradoxes across 18 different domains. Vogt's framework acts like a massive computational stress test, and the scientific impact is absolutely staggering. By simply applying bounds to accumulation, it tackles these impossible paradoxes. For the Riemann hypothesis, it provides spectral density control. It actually explains mathematical smoothness in the Navier-Stokes equations for fluid dynamics, and it even addresses the Yang-Mills mass cap confinement in quantum physics. We're talking about divergences that stumped scientists for literally decades, suddenly bounded and saturated.
Okay, jumping into Section 4, Stabilizing Giant Launch Vehicles. Basically, where math meets heavy metal.
So we are taking that exact same structural safety switch that applies to prime numbers, and we're dropping it straight into aerospace engineering. In modern spaceflight, we see these persistent, nagging inefficiencies when scaling up. Merely pumping more input energy into massive systems like SpaceX's Starship, ESA's Ariane 6, or India's LVM-3 pushes them right out of the regulated efficiency plateau and straight into the unstable saturation zone. You just do not get proportional gains for the energy you're putting in.
Look at this. The sublinear velocity gains are undeniable. Taking the Falcon 9 as our baseline, moving to the Falcon Heavy requires a massive 200% increase in thrust, but you only get a 29% gain in velocity. And for Starship, a 224% increase in thrust only gives a 17% velocity gain. It's crazy. You literally cannot just slap a bigger engine on a rocket. The entire coupled system, mass, energy, thrust, trajectory, needs constraint-regulated math to stabilize it. Without the AM-regulator, increasing capability in one area just accelerates a bottleneck in another.
Which brings us to Section 5, Macroeconomics and Zero-Latency Computation. The human impact.
All right, we've scaled from quantum states to giant rockets, so let's shift focus to human-scale systems. Just let this massive number sink in for a second. 2 to 3 trillion rupees. Using real-time macroeconomic data, Vogt applied the AM-Regulator to the government macro system of India. The result? An estimated fiscal stability gain of 2 to 3 trillion rupees. And it scales to global financial systems too, estimating roughly $1 trillion in systemic loss avoidance during crisis shocks. It basically acts as an instantaneous safety net.
So how do we actually pull off this massive stability? It really comes down to absolute computational dominance. While legacy systems rely on these clunky, iterative, fragmented models, the SRA software suite uses zero-latency, closed-form spectral compression. Operating instantaneously across 50 countries, it consistently compresses instability by 40 to 60%. It doesn't sit around waiting for a crash to happen, it regulates the data in real time.
Finally, Section 6, a universal structural law. Let's tie it all together.
From the spectral geometry of math, to the thrust of giant rockets, to the volatility of global markets, it all leads to this profound insight from Savio Antonio Vogt. Divergence across complex systems arises primarily from unregulated aggregation rather than intrinsic instability. The universe doesn't inherently want to break down into chaos. It fails simply because accumulation is left unregulated. Introduce the structural safety switch and system stabilize. It's really that elegant.
So, I'm going to leave you with this provocative question to ponder. If a single constraint-regulated law truly governs the entirety of the natural and constructed world across all scales, what impossible limits are we going to redefine next? It challenges literally everything we thought we knew about the boundaries of physics, engineering, and economics. Thanks for joining me on this explainer, and keep questioning those limits.